Swayam Prabha. Digital India. Educated India.
So now we'll go, if it's clear, we'll go to loop, like register allocation with 4 registers for loop. So here we have a loop where how it is a loop. We have 4 basic blocks, B1, B2, B4, B3, and please note that the conditional statement is not added in the, like, each loop ends, each basic block ends with a conditional statement to bring out the difference between LLVM IR and this basic block. Like LLVM IR, initially you'll have a 5 block if you have a junction like what is the value of the variables coming at a node which has a basic block which has 2 predecessors, that will have 5. Then the basic block will end with a conditional statement or a jump statement. So that is avoided here. So why this is a loop? Why this is a loop? Which edge makes it a loop?
P4 to B1.
Yeah, P4 to B1, it's a back edge, right?
Yeah.
So it makes it a loop. Now in this loop, you want to use some heuristics to have a better register location so that the performance is good. So here it's already given, like B, C, D, E, F are live out. B for B3, B, D, E, F are live out. What is live out? What is the meaning of live out?
Live at the end of the basic block.
Yeah, what is actually then meaning of live means?
Their value will be used in the future.
Yeah, the current value of these variables will be used before it is defined again. Before it is defined again, that's also important. Like, so B has a value now, its value will be used in some of the successor blocks, which is not shown in this diagram. And this value of B will be used. So because that means before the B is redefined, it will be used again. Same for C, D, E, F, and C. So now I want to compute the live in for B4 and live in for B3. What will be live in for B4 and B3 then? Let us come to B4 first. What will be live in for B4? Is there any change? Live in for B4 and live in for B3. This is the live in for B4, right? B is removed here. Why B is removed? Because the value B is defined in this statement, so the value which is coming will be modified. So value of B is coming from the previous or the predecessor of B4 will not be used here, and here it will be B and E removed, so it comes here. So then what about live in of B2 and B1? Like so the live in of every variable. So live in B1, B, C, D, F. Live in B1 is A, C, D, F. Live in B2 is A, C, D, E. Live out is C, D, E, F. So I hope things are correct. The values are correct, I believe. So here B is killed, but D and C is as a use. Here at B2, A comes as an additional live in, because there's a minus D. A comes as an additional live in, and for B3, like A comes in, like A, C, D, F. E is removed because B is killed, and B also removed because B is assigned. I hope this covered in data of analysis or any previous prior lectures.
Yes, sir.
Yes. What? Yeah, just covered because in case anybody has missed. Yeah. Now this is a loop. Now I want to do register location with 4 registers. So how you can save a cost or how you can have optimal coordination with some heuristics. So we have studied register location with graph coloring, and even you know that it does not have a polynomial solution. So we'll use some heuristic. Using usage count, some heuristics are used. So this heuristic which is I'm mentioning is like assuming variable x is in a register, we count a saving of 1 for each use of x in loop before it is redefined. So if a value which is available in the register is used before it is redefined, we'll count a saving of 1 because the value is used again. So we will count a saving of 1. Saves 2 units if we can avoid store of x at the end of basic block. So at the end of the basic block, if you want to store a value, why you need a store? Number of registers available may not be enough for the number of variables. I hope you got it. So it saves 2 units if we can avoid store of x at the end of the basic block. Benefit of allocating a register to a variable x is defined by the formula below, like the heuristic. It's not like a proper solution that we are going to use. Benefit of x is sigma of all b in L use xb plus 2 into live x comma b. So what is the actual indication about live is that the value will be used again in future. So now use xb is actually defined by this formula. Use xb is the number of times x, the variable x is used in b prior to any definition of x. This prior to definition of any x is important. Use of xb is number of times x is used, where x is a variable. X is used in b prior to any definition of x. Live xb is in 1 if x is live on exit from b and is assigned a value in b. This is also important, is assigned a value in b. So based on this formula, like if you note down this, benefit is use of xb plus 2 into live xb. So what is use xb is number of times x is used in b prior to any definition of x. Live xb is 1 if x is live on exit from b and is assigned a value in b. So then what will be the benefit for variable a in this figure? So if you look at that formula, like so I'll go to the formula again, like use is x is used in b prior to any definition of x. Live x is 1 if x is live on exit from b and is assigned a value in b. So we look at the second condition. Which are the basic blocks which a is assigned? Only in b1, right? And whether a is live on exit from b1, and look at the live out. A is live on exit from b1, so you will have a value of 2. Whether this use will count for this heuristic function, like the so use x is number of times x is used in b prior to the definition of x, but this will not count, so that like this will not count because a has been already defined. So you have a value of 2 for this basic block b1 for a. Then any other basic blocks where there is a use of a prior to definition is b2 and b3 has a definition of use of a. So the cost or the benefit of x will be 4. And so in this figure, which variable will have the highest benefit? here, which variable will have highest benefit. So
Is it D?
D. So what is the value that you have found out for D?
No, I didn't like calculate it. And just,
Yeah. You can see like D is defined and it's live on active. So here there's a cost of you you have a benefit of 2. That is live out of D1, D is there, and D is defined, so it will have a value of 2. And there are like one definition, one use here, and one use here. So is it 5 or 6? If you look at live in of B1, B, C, D, F is there, and you have a use of D before it is defined. Look at the statement, D assigned to D minus D. Before D is defined, D is used. Hope it's clear. The incoming value of D is used before it is defined. So live in of B1 also contains D. So it will have a value of 1. So total value will be 6. Yeah, we look at the values. Benefit for A is 4, B is 5, C is 3, D is 6, E is 4, and F is 4. So, so if you want to have a allocation for this loop, it's limited number of registers. You have 3 registers. So B and D can be allocated. What about the third register? You can choose among A, E, and F. Okay. So this is the globalization allocation that we are looking at. So, and this is the generated code. So with R0 equal to A, R1 equal to B, and R2 equal to D. So R0 you selected A. So this there is a prologue and epilogue. So here there is a load of R1 of B and R2 of D. Because you look at these registers, B, C, D, and F is there as live in. So this basic block, here there is a load of R1 and B and R2 of D, because it is used in the immediate, the first basic block B1. For C and F, where is C and F? So you have a C loaded here, F loaded here in D4 and D3. Because F is coming here, C is coming here. This is a new basic block, or a new, this is not part of the loop code, but it's added just before the loop, because this loop ends with the brackets B4 to B. So you load in R1, B, and R2, D. Then load R3C, add R0, R1, R3, subtract R0, R1, R3. So whenever you have a register that is a variable which is not allocated in a register, you use R3. So here we are using 3 registers, and addition, like total number of registers in the machine is 4. We are assuming total 4 registers are available. So 4th register will be used for just loading the one of the operand which is required for the operation. So add R3, R0, R3, store ER3. This store is required because the result is computed in R3, symmetry stored. And similarly, you have of load R3F, add R1, R2, R3, load R3C, sub R3, R03. And look at this this epilogue, like when you exit from the basic block, the variable which are live, you are just storing, like B, R1, D, R2. So these values are computed in R1 and R2. And other live variables like F, E, they are already stored in the memory. So R1, R2 is storing. R1, R2 is storing. So it can be assumed that A is not live on exit or live out. So here, this lecture, the intuition was that when you generate a code for a machine, it could be like a complex machine with superscalar architecture or even multiple cores or whatever it may be. So such a code, the code generation is more complex. Which instruction to be used for a given sequence of code? So that is a very complex procedure. So in that scenario, the coordination becomes more complex. For example, suppose you have this machine ideas. So what I would like to mention is, or ask, just 1 minute. So what I would like to mention is, in such a way, like coordination is tough if the hardware becomes tough. So you know this risk and CISC architecture, right? What is risk? What is the difference between risk and CISC?
The instructions in a RISC architecture are simpler.
Yeah, and also the number of registers in risk and CISC. So what about complex instruction sets? So coordination will be have different requirement for risk and CISC, and the optimized coordination is not that easy. And sometimes even for a given architecture, whether it supports 64-bit or a 32-bit floating point operation, so this type of hardware dependencies are there for the same vendor. So if you look at the different processors, the requirement will be different, but you should understand that these fundamentals like liveness analysis, then register allocation, then finally printing the assembly, they are fundamental part. So I covered it with some basic example where you have a simple machine. And instruction selection is also an important factor. For example, this machine idiom. Suppose you have A equal to A star 2 as a expression. So what will be the machine instruction that you would prefer to have that operation to be done? A equal to A star 2.
You can convert it into an addition because addition will run much faster compared to multiplication.
Yeah. So is there a better way?
You can make it a shift, a left shift.
Yeah. So in that case, should know like how many clock cycles each instruction will take, and which will be more beneficial. And also when you have number of registers is very limited and you have enough variables, a lot of variables are not sufficient for the registers. You should be selective in which register to be used for which variables, especially with loops. Loops are targeted for targets where most of the time is spent on execution. So in that case, like software pipelining where you unroll the loop, those functions have been covered, I believe, with respect to this superscalar architecture, even pipelines, multi-stage pipeline. So, but here is totally different way of the fundamental operation being in the coordinate instruction selection, liveness analysis, register allocation. Then one more question is, once you do register allocation, will it be in SSA form or? So you have studied SSA form. So what is SSA?
Sir, are you showing some other slide deck? Because we are not able.
No, there is no other slide. So the presentation is 1 minute. Is it visible now?
We just see loop global register allocation slide.
Yeah. Okay. Yeah. So and there is this people optimization. So that is a machine dependent optimization. So optimization done on a small set of compiler generated instructions. So here, that's what I'm mentioning about instruction selection, and after instruction selection being done, whether more optimizations are possible. So this is with respect to backend. So that's why I asked about this interactive questions with respect to some small ways of how you should schedule the instructions, how you convert one instruction to another. Like suppose you have something like A equal to A star 2. Initially, you had some multiplication, then you want to modify to addition or left shift. So So optimization is done on a small set of compiler generated instructions. It's like peep-code optimization. The small set is known as small set of compiler generated instructions that is known as peep-code. So the next tag I will be covering fully on LLVM. So where these fundamental like liveness, register allocation, what should be clear, and this is covered independent of LLVM, so that is very generic, and its reference is Dragon book, like Rahoseti Ullman book, where there's a separate chapter on code generation. It's difficult to cover in 1 hour. There is content for instruction selection, so many things. So this lecture will motivate you to read the chapter, like, and so I want to ask. So I was asking about SSA form. What is SSA?
Single static assignment.
Yeah, static single assignment form.
Yeah, a static single assignment.
So what is the speciality about that?
Every variable is defined only once in a basic. So we define one variable for once,
Yeah.
and we can use it. But we can define one variable for one, but we can use it as many times we want to use.
Yeah, for every variable there's only one definition, but multiple uses, right?
Right.
Yeah. So once you do register allocation, it will be the case that in the generated code will be like SSA, like each register is assigned once, because you in the case of SSA form there are enough number of virtual registers or temporaries, like that percentage, 1%, you see. But here when you come to code generation, there's a limit on number of registers, and so how you will handle the optimization is totally different. So till now we have seen LLVM IR with in SSA form, right? And with generic instructions like add, mul is target independent. But when it comes to the code generation, all the instructions are hardware dependent. And you look at the coming lecture in that aspect, where these concepts like SSA may not hold. The instructions are hardware dependent, and what are the things, how the LLVM does it, like. So this concept like live variable, liveness analysis, and instruction selection, is important in that.